Hello everybody, and welcome to the video on ChiSquare test for independence. So let's start out with, first of all, a quick look at the test for independence. If you need to, you can pause the video here, take a picture of my formula sheet like I always say to do in my videos, and we'll get going. You see, the ChiSquare test of independence, we start with the null idea of two categories are independent. So what this is we're going to look at two categories and decide are they independent or dependent. And how we're going to measure that is by stating in the null, as far as I know, the two categories are independent. The H1 then will be the opposite, which is the two categories are dependent. So I'm assuming the null is true until you give me enough evidence to say that they're dependent. How I measure that evidence by calculating out the chi-square statistic, as you see here, and utilizing the critical value from the chi-squared inverse function. So let's get right into it. Here's our problem. Got it. So the problem, I always like to go through my steps of solving any type of hypothesis test. Step one, you should be able to give me your H0 and your H1. Well, your H1 is I'm going to assume the cats are independent. What I mean by that is I'm assuming the category is independent. That is the age of a person and how they get their primary source for news. I'm going to assume that's independent. The age of the person and the primary source for news. I'm going to assume that until I'm going to show in my alternative the cats are dependent. The categories are dependent. So how do I do that? I must run a chi-squared test for independence. So second level, you need your test statistic. So what is our test statistic? Well, our test statistic is based off of two numbers, F0 and FE, and what they represent. FE, that is. So what is F0? F0 are your observed values. So what I'm going to do up here is just pretty much copy down my observed values in a very, very particular order. So I know the first, 5 are all about the age of under 36. The next 5 are all about the age of between. And then the next 5 are all about the age of 50 plus. If it's better for you to describe them right here, that might be something you might want to do, is describe them so you understand what each represents. What I mean by description is, what is the 107? The 107 is under 36 and local TV is how they get their news. All right? You describe them. All right, so that is what I call the observed values, the data you actually pulled from your survey. We surveyed 1,434 people, and this was our results. These are our results. Now, what would be expected? Well, you have to understand a little bit about probability theory to understand expectation. So to understand what's expected, simply put, is if it's random and universal how people are picked, independent, then what you can say is the expected frequency would be the number of people in local TV, getting the news from local TV, times the total number of people that are under the age of 36, divided by the grand total. This would be expected, all right? It would be if regardless, if you're independent, that if age and TV are independent, this is what's expected coming out from basic probability theory, is you would look at the total of local TV times the total of age, that's the independence factor, divided by the 1434 to get an expectation. And that is our number, 100.64. And as you've watched my videos before, I have to create this statistic. The statistic is F0 minus FE, which makes sense, right? To compare observed versus expected, you would subtract them. Potentially, there could be a negative offsetting our formula, and that's why we square. But once you do a square, you're out of the wrong units, so we divide by FE to make sure we're back into the proper units. So again, I will take F0 minus FE, square it to make it positive in case there's a negative, and divide by FE to make sure I'm back in the same units I started with. Units being, if you square, you're in different units. If the units were miles, you'd be in square miles, and you can't compare miles to square miles. That's why we divide by the FE to get it back into the proper units. I'll copy this formula down, and what I need to do is I need to now write this out, this formula out. And to me, there's no quick way of doing this in Excel unless I set this up perfectly. But it's good to teach you guys what I'm going to do. For 73, the row total for 73 is there. Now I'm going to multiply that. We're going to multiply that by column total. And we're going to divide that by total. There are some ways you can eliminate some work, but might as well show you. 75. 75 is in this row total. Multiply it by the column total you're in, and divide by the grand total. That's the common math we do over and over again. Hey guys, welcome back. So I paused the video and I decided I might as well do the math out for you guys in these examples, so that way you didn't have to watch me do it over and over again. And so what you have here is I calculated out the expected for each one of these. Again, using the row column and the total column divided by the grand total. All right, row total divided by column total divided by grand total for each one of these. So you should be able to check my numbers. Now what I do is I like to check my work. My observed should match the number in my survey. The expected should also match that. These should always match. That tells me I wrote my code correctly. Then I create my formula out, and I got a statistic of 2218. Now the question becomes, is that enough? Is that enough to get into the rejection region? Well, to understand the rejection region, you have to understand the chi-squared, and that's why I'll bring up my little picture. So what's going on is we draw a chi-squared function. In this case, this is a 2 degrees of freedom chi-squared function right there. If you change the degrees of freedom, you change the curve. You kind of bring this down a little bit, make it more normal each and every way. All right. So, but this one is a 2 degrees of freedom. They all work the same way though. We put a bar in the sand. If you cross the bar, then you're going to reject at that level of significance. If you don't cross the bar, you don't have enough evidence and you do not reject. Whatever you write to your level of significance is, that is your alpha, then 1 minus alpha will be the area underneath because they have to add to 100%. So alpha goes here, that's your rejection level, and 1 minus goes below it. To find this value out, we're going to do an awesome advanced calculus to do with the derivative of the integral to find this out. No, we're actually not going to do it. Excel's going to do it for us. Thank you, Excel. Excel has this function called dot inverse. If this is a normal curve, I do norm S inverse. If this is a T curve, I do T dot inverse. This is a chi-square curve, so I'm going to do chi-square dot inverse. What chi-square dot inverse asks is, which curve are you looking at? That's where the degrees of freedom will play in. That'll tell me the exact chi-square curve I want. And secondly, it's going to ask how much area is below. Every one of the inverses is always about in area below. So let's go to the Excel code now. So first, I need the degrees of freedom. Well, in a chi-squared independence test, the degrees of freedom are row minus 1 times column minus 1 multiplied. In this case, 4 times 2. And that makes sense because we have 2 categories. The first category is news. And so we take minus 1 of that. That would be 4 categories left. We have age as the other category, and minus 1 of that would be 2. And that's why we have 2 categories in a multiplying situation because of the independence. And we do 4 times 2. And that gives us 8. Again, that tells me my degree of freedom is 8. My curve I'm picking is a chi-squared curve, degrees of freedom of 8. That goes into my inverse function. Degrees of freedom is the second number. Now, I like to automate it. My alpha was 5%. Why? Because I picked it. It didn't say it. In your research, you got to pick it. 1%, 5%, 10%. You got to decide what is your type 1 error level. That's really what you got to decide. Alpha corresponds to the probability of a type 1 error. So you got to decide how much you want that to be. Let's say we set it at 5%. And so then notice the 1 minus, because chi-squared inverse needs the area below, which would have been the 95% according to my picture again. 95% below. Rejection at 5% means 95% below. I need you to understand, not just plug and chug, I need you to understand why I'm doing it. All right, once we got these two numbers, the statistic and your critical value, you can make your conclusion. Since my statistic is above the critical value, you're going to reject. That's always true. If your statistic is more than your critical value, you always reject H naught. What does that mean? We'll go back up to H naught. H naught, we assumed they were independent. Well, I'm now rejecting that statement, which means I believe the categories are dependent. Well, if we're going to make sense out of that, that means age and news are related. How people get their news and their age are related. That's my statement. I've done a large-scale study, and I believe the categories of age and news are heavily related at a 5% level of significance. Okay, that's what we have. Now, on top of it, some cooler things. First of all, can you determine what are the most important ages or ways of getting the news that affect this result more? The answer is, that's why I love Excel, because some advanced programs don't give this out. I love Excel because it actually, this number here is kind of, when you add all these up, right, you get your test statistic. I think of this as the material witness. How much was each variable affecting the total result? I've already highlighted in yellow the two biggest ones. This one right here was 8 points. This one here was almost 12 points. That is enough to almost beat my critical value on its own. Notice the two numbers in yellow are almost enough to beat it on its own. I can highlight the 3 too, and I would have beaten it. So that means just these 3 alone are enough to beat and make me reject. So let's go check them out, shall we? I didn't have the 52. But right here, these 3 elements, and that's why it's important to mark them, 52, 95, and 76 in my chart. These 3 elements are key indicators of how things are different. And if you look at it, yes, it's obvious. Newspaper. How many people under the age of 36 read a newspaper? Obviously, it's disproportionate. Vice versa. How many people get their internet news for the age bracket under 36, and how many people over 50 get their news from the internet? It's a clear, decisive victory in why there is a difference between age and how they get their news. So it's not, a big barnstorm type of answer, but at least it's a good example of working through. By the way, this is not red for any reason. You can get rid of that. That was just me playing around with something earlier. Cool. All right, guys. Now it's your turn to do it. So pause the video and try it out. All right, we're back. So as you can see, what do we got here? A researcher has prepared a set of silhouettes of body shapes listed above. He asked both females and males which picture was the most attractive. So the question is there evidence of a difference between women and men in this scenario? Because this is all about attractive and body images, right? How do body images and silhouettes, it's kind of like an outline of the body. Do men and women view images differently? So, first of all, what you had prior in the video was there's no totals. I've now changed it to totals. You need the totals because that's how you find FE. So you have to create the totals. If you had a pivot table, it would have already created the totals for me. And in fact, and to get prepared for a chi-square test for independence, I'd run a pivot table analysis and get this whole table easily. All right, this table is something a pivot table can build quickly and efficiently in Excel. I need these totals because they're going to help me build the FE column. Remember, all right, F naught are the observed values, and I wrote them in row order. FE are the expected values. Once again, expected is row total times column total divided by grand total. I got tired of writing row total, column total, so I made a row total and column total column. That way I can easily just write a code that does it, where the grand total doesn't move, it's 140. So once I had the formula in, I could just kind of move it down quickly. This is a reason for advanced programs, by the way. RStudio, which is a free program, you don't have to do any of this work. It does it for you behind the scenes. Not so much in Excel yet. You have to kind of write this out. Now, as a teaching point, I like writing it out. I like seeing how each piece comes together and how each piece adds together to get my test statistic. There is my test statistic. Now, is that enough to reject? I don't know. But I can tell you right away, that who plays the most in getting that 9? Right there, the 2.2. So right away, I can pinpoint 2.2 is the highest individual sum I have over the total. So this factor here would play the most if they were dependent. This number right here is the one that seems the most out of whack, the 11. All right, because it has the biggest total. Notice the second biggest total, 165, corresponds to the female point of view. So this right here, if there was any chance of these to be dependent, that there's a relationship between their opinions, then you would see this in this column because of how this came out in the numbers. Remember, this is their individual weight. When you add this up, you get the total weight, and that total weight is the chi-square statistic. All right, so it's time to run the rejection region again. Well, the rejection region is based on degrees of freedom. My degrees of freedom here, well, we have 1, 2, 3, 4 columns. Minus 1 would be 3. Times, we have 2 rows. Minus 1 would be 1. So the degrees of freedom would be 3 in this case. So we're looking at chi-square degrees of freedom of 3. My alpha, let's say we had, once again, a good old 5% level of rejection. That means my chi inverse, that is my chi-squared inverse, make sure you get the right one, my chi-squared inverse has my probability of, let me make sure I write it right, 1 minus alpha. Remember, you need the area below when you're using dot inverse, comma, degrees of freedom. You need to tell Excel which curve to calculate for. And it gives me a 7.81. Once again, we've crossed the bar. Once again, I will reject in my 4-step process my result. Once again, I have my statistic. All right, my statistic is 9.129. My critical value was 7.81. So bottom line, my answer is, so this would be your critical value. My statistic is greater than my critical value, and so I reject at a 5% LOS, 5% level of significance. And what does this mean? There is a dependency in body image and gender. There is a clear dependency in body image and gender according to this study. Awesome. That's it, guys. Now, of course, we could check to see if I change alpha to a different level, would it change your results? In changing alpha, that would be only right here. Let's change it to a more extreme 1%. Let's see what happens. Whoa, if I change it to 1%, notice what happened. My statistic is no longer bigger than a critical value. My statistic is no longer bigger than my critical value. So I would have to report my statistic is under the critical value, and so I do not reject at a 1% level. Okay? I would have to say my statistic is less than my critical value, and so I do not reject at a 1% level. So at a 1% level of significance, I don't see a difference between attractiveness according to shapes and gender. This is a great example where you tell me your alpha, and that's going to define your answer. It's very important to define your alpha in the beginning, because if you change it at the end, you're changing your answer because you want it to fit your answer. That's not good. Another way to look at this, though, is my test statistic is dependent of alpha. That's another way to look at this, okay? My test statistic is clearly dependent on alpha. If I change my alpha to 11%, all right, I go from reject to do not reject. That's important in theory, is I go from reject an HNA to do not reject based on that alpha change. That's an important thing to discuss when you're looking at your research. At a 5% level of significance, we definitely do reject. Let me get my results right. At a 1% level of significance, we do not reject. So alpha is sensitive, all right? My data is sensitive to alpha. So we got to be careful of that. All right, guys, and that's how you check for independence among two category variables. Thank you for watching this video. Stay tuned for others.